if we denote in this case ui, okay, as the average value between I delta x and I plus 1 delta x. So this is like we have split the space, let's say 0 and delta x and 2 delta x. The average between here is going to be called u0. And the average between delta x and 2 delta x is called u1. The average over the next interval is going to be called u2, etc. Okay? In finite volume, we actually denote the interface values because the interface values are actually not the primary variable we actually store and solve. So it's interesting, people usually denote the interface values of u using fractional subscripts. So the interface value between u0 and u1 is denoted as u half. Okay, u half is going to be, it's no longer going to be an average. So this is definition, right? U half is denoted as the u at actually delta x. So let me actually write it a little bit more general. ui plus half is actually ui delta x. I mean, this is a little bit counterintuitive. Not I plus 1, I plus half. This is a little bit counterintuitive because why am I using a fractional subscript to denote the value of u at an integer multiple of delta x, right? I mean, that's exactly, that's not the same thing we use to denote a value in finite difference. In finite difference, u at I delta x would be denoted as ui. But here, remember, in finite volume, the value at the grid points are actually not something we store in computer. It's something we actually approximate, use the neighboring volume averages, right? Okay, so we adopted this notation, which may be counterintuitive if you come from finite difference, as all of you are. But this is really the more intuitive notation to use in finite volume because the fractional indices are not the primary variable to use. So for example, one example of what we can do in finite volume is we approximate ui plus half as the average of ui and the ui plus 1, right? Just to take the two volume averages. It's like over here, right? Here, the value of u at delta x is actually u half. The value just in between these two grid points are u1 and half, right? So it seems quite intuitive to approximate the value at interface as the average between the two neighboring volume averages. Okay, and another example is we are going to approximate a du dx at the interface I plus half. How about this? What do you think we can approximate this as? Right, this is another thing we need to approximate. Any suggestions?
Could you do the derivative at I plus the derivative at I plus 1 over 2?
Yeah, I can do the derivative at I and derivative I plus 1 averaged, but I don't actually know the derivative at I and I plus 1. All I know is the volume averages at the ith interval and the I plus 1 interval, right? So essentially, what I'm trying to approximate is the slope, right, So what is the slope here? What is the slope here, right? I approximated the value. Now I need to approximate the slope.
Can we just use the difference, like u2 minus u1 divided by delta x?
That's an excellent suggestion. How about just the ui plus 1 minus ui divided by delta x? That's actually the most popular approximation of the derivative in the interface. So why are these appropriate, right? In order to convince yourself these are appropriate, you have to do two things. Well, one thing is actually pretty standard. That's actually a Taylor series analysis. Okay, you have to figure out, okay, if I have a very smooth function whose high order derivatives are small, and when my delta x is also small, is this a good approximation? Which means, is the truncation error of this approximation small? Okay, I mean that we did this in finite difference, but let me just show you an example of how to do this in finite volume, right? So actually, this is not okay. Let me actually show you how to do this in finite volume.